In this screencast, we are going to go over correlation analyses and simple regressions. We will start off by going over correlation analyses. When conducting a correlation analysis, there are two assumptions that must be met. The first is that the variables need to be normally distributed. Please refer to the video on central tendency for more about this. The second is the homoscedasticity assumption. For more about this, please refer to the video on multiple regression analyses. The current data set we have contains a measure of body fat. The measure tells us the percentage of body fat that the participant has. The second measurement we have in the data set is TV viewing, and this refers to the average hours of weekly TV viewing of each participant. We are interested if there is a relationship between body fat percentage and average hours of TV watched per week. That is there a correlation between the body fat percentage and the average hours of TV watched per week? Both of our variables are used in a ratio scale, thus we can use Pearsons' correlation coefficient to test our assumptions. To do this, please click Analyze. Click Correlate. Click Bivariate. This opens up a new window called Bivariate Correlations. In this window, we will tell SPSS the details for a correlation. Click Body Fat and click the central arrow between the variables you have and the box labeled variables. Click TV Viewing and click the arrow in the box between your variable and the box labeled variables. This has moved the variables that you want to include in the analysis underneath the variables box. This means that SPSS will use them in the correlation. As you can see in the box labeled correlation coefficients that is currently highlighted, we will be running a Pearsons correlation. The Kendall's TAW-B and the Spearman correlation are used for non-parametric tests. We must also decide if we are going to use a one-tailed or a two-tailed test. A two-tailed test is used when you do not have a clear hypothesis, and a one-tailed test is used when you do have a clear hypothesis. For example, that you think that higher body fat would be related to higher TV viewing. For the sake of this video, we will go ahead using a two-tailed hypothesis. Click OK. This has opened up a new window labeled Output, and this displays the results of your correlation. As you can see here, I have highlighted two boxes in yellow. These boxes display the same results, just on different lines. And I have highlighted two boxes in blue. Again, these boxes display the same results, just on different lines. If we look at the box labeled body fat on the left, we can see if when we look across that it presents the same information as if we look at the TV viewing. Therefore, to go through the results, we will just focus on the box labeled body fat. The yellow box, outlined in red, that says Pearson correlation, refers to your R value. For body fat, the Pearson's correlation with body fat is 1, and that is because they are the exact same variable correlating with themselves. If we look at the TV viewing, it is 0.636, so that tells us that we have an R value of 0.636. The current box, highlighted in yellow and outlined in red, gives you the p-value for your results. It tells you if your results are statistically significant. The current box, highlighted in yellow and outlined in red, refers to the n-value and tells you the number of participants that were included in your analysis. This slide shows how you would report the results for a correlation. In this instance, the correlation analysis indicated a significant relationship between body fat percentage and weekly hours of TV. The 8 in brackets refers to the degrees of freedom. Degrees of freedom in correlation analyses are calculated as n minus 2, with n referring to the total number of participants. In this instance, we had 10 participants, so 10 minus 2 is 8. 0.64 refers to your R value, and P refers to your significance value. Since P is less than 0.05, the P value is significant. TV viewing accounts for approximately 41% of the variance in body fat percentage in this sample. The 41% was calculated by taking the R value and squaring it, 0.64 times 0.64. We will now go over how to conduct a simple regression using the same data we used for our Pearsons correlation. In this instance, rather than asking, is body fat percentage correlated with number of hours of TV watched per week, we will ask a more direct question. Does the number of TV hours watched per week predict body fat percentage? Click Analyze. Click Regression. Click Linear. This has now opened up a window called Linear Regression. Click Body Fat, and then click the arrow next to the word Dependent. Click TV Viewing, and then click the arrow next to the box labeled Independence. Click OK. This has now opened up an output window displaying the results of your regression. As you can see in the highlighted boxes, your R value is the same R value that you had from the Pearsons correlation, and your R square value is the same value that you calculated when you squared the R from your Pearsons correlation. The ANOVA table displays an F value, which examines whether the regression model has a statistically significant predictive capability. As you can see here, the significance column has a value of 0.048. Since this is less than 0.05, it is statistically significant. The box currently highlighted in yellow shows the standardized and unstandardized coefficients. The unstandardized coefficient displays the predictive effect of the predictor value in the units that this predictor value was measured in. In this example, the units are hours of watching TV. In contrast, the standardized coefficient displays the predictive effect of the predictor variable in standard deviation units. In the highlighted box, the t-value evaluates the statistical significance of the predictor variable by dividing the unstandardized coefficient of the predictor by its standard error. The statistical significance of this t-ratio is displayed in the significance column to the right. The current box, highlighted in yellow, reports the 95% confidence interval. If we were to draw randomly 100 samples from the same population, in 95 of these 100 samples, the unstandardized coefficient of the predictor would be somewhere between the values reported in the lower and upper bound boxes. The current slide shows how you would report the results for a simple regression. The regression analysis indicated that the hours of weekly TV viewing significantly predicted the percentage of body fat, accounting for approximately 41% of its variance. The statistics reported here are taken from the ANOVA table on the results page. The degrees of freedom are also taken from the ANOVA table. One way to display the results of your simple regression is in a scatter plot with a best fit line. We will now go over how to create a scatter plot using the same data we have been using for the entire screencast. Click Graphs. Click Chart Builder. This has opened up a window labeled Chart Builder. Click OK. This has opened up another window labeled Chart Builder. As you can see, your variables are located in the top left-hand corner, and the graphs we have to choose from are located in the bottom left-hand corner. Click Scatter/Dot. Click Simple Scatter and drag it into the box underneath this label Chart Preview uses example data. Click TV Viewing and drag it to the box labeled X-axis. Click Body Fat and drag it to the box labeled Y-axis. Click OK. The scatter plot showing the data is now displayed in the output window. As you can see, TV viewing is on the x-axis and body fat is on the y-axis, and the dots representing each participant are scattered throughout. In order to get the best fit line, please double-click on the graph. Double-clicking on the graph will open up a new window labeled Chart Editor. Right-click on the graph and then click Add Fit Line at Total. This will open up a new box labeled Properties. In this box, you can choose your fit method. The default linear is the method we are choosing, so all we need to do is click Close. Our line has now appeared on the graph. In Chart Editor, if we wanted to make more edits to the chart, we would stay in this window, but since we do not, you simply click the X located at the top right-hand corner. Our scatter plot now displays the line. As you can see in the highlighted yellow box in the top right corner, r squared linear is equal to 0.405, the r squared value that our simple regression gave us. This now concludes the video. In this video, we learned how to conduct a correlation, a simple regression, and how to create a scatter plot.